Hello everyone. So in this video, we're going to be trying to attempt one of the AP Physics B, the old AP Physics exam, the 2010 free response question 1. Right? And I want to do this because it's a good example of combining our concepts of kinematics and integrating our concepts of work, power, work, energy, and momentum. All right, so let's get started. It's from the 2010 exam. All right, so let's start. Block A of mass 4.0 kilograms is on a horizontal frictionless tabletop and is placed against a spring of negligible mass and spring constant 650 newtons per meter. The other end of the spring is attached to a wall. The block is pushed toward the wall until the spring has been compressed a distance x, as shown above. The block is released and follows a trajectory shown, following 0.8 meters vertically and striking a target on the floor that is a horizontal distance of 1.2 meters from the edge of the table. Air resistance is negligible. So let's find part A. Calculate the time elapsed from the instant block A leaves the table to the instant it strikes the floor. All right. So one problem we have is we don't know this velocity v, right? However, that is only, if you know from kinematics, that is only the horizontal piece of the velocity. The vertical piece has nothing to do with this v value. All right? So if we want to find the time it takes, let's use one of our kinematics equations, especially this one. Delta y equals v naught y delta t plus half ay, or I'll just go g t squared, okay? Now v naught y is 0. That means this term cancels out. So we're left with delta y equals 1/2 g t squared. Okay. Now then we can get delta t equals square root, so we multiply both sides by 2 times delta y over over g, right? That gives us 2 times, well, negative 0.80 meters, because it's falling downwards. So delta y will be negative over negative 9.81. And we get a delta t of, let's put this 2 times negative 0.8 divided by negative 9.81, negative 9.81 square root. Takes us about 0.403 seconds. All right, so that's the answer to part A, 0.403 seconds. So we're asked to calculate the speed of the block as it leaves the table. Okay, so this is part A. Part A. So now we're on part B. Right? Now I'm in space here, so I'm going to try to use the resources I have with me. So if we use a definition of velocity, Vx equals delta x or delta t, you just solve for delta x, multiply both sides by delta t, or actually we don't even, you don't even need to do that. Yes, so that's Vx equals, well, delta x will be 1.2 meters. It will travel 1.2 meters to the right And it'll take, well, it will take 0.403 seconds, the time we got in part A. And then using that, we can get our horizontal velocity. So 1.2 divided by 0.403, it's not even 403, it's 404. Excuse me, sorry for that interruption. So it's not even 0.403, it's 404. So it's 404. Just erase any stray markings I may have made. Make sure all my space is clean. All right, so if we divide through, we get 2.97 meters per second. Right? 2.97 meters per second. Right? And part C, calculate the distance x the spring was compressed. Okay, so this is basically conservation of energy. Because they give us, it's a frictionless tabletop, all right? So when they compress it, initially, there's elastic potential energy, right? From the spring, or spring potential energy. Then it gets converted into its maximum kinetic energy. So we can just, we'll just set both of these equal 1/2 kx squared equals 1/2 mv squared. 1/2s cancel. We have kx squared equals mv squared. And if you want to find x, you divide by k, then take square root. So mv squared over k. That equals, well, mass is 4.0 kilograms. And that's v squared, so we got v is 2.97 meters per second. And then square that over our spring constant, 650 newtons per meter. All right. And that gives us about, let's see what we get. 4 times this squared, just using my calculator. So very close to this. That divided by 650. Right, divide out, square root, and we get 0.233. So, right, just need to add the answer there. 0.233 meters. 0.233 meters. Okay. So here's gets a little trickier. Okay. So let's move on. Block B, also mass 4 kilograms, is now placed at the edge of the table. The spring is again compressed a distance x, and block A is released. As it nears the end of the table, it instantaneously collides and sticks to block B. The blocks follow the trajectory shown in the figure below and strike the floor at a horizontal distance d from the edge of the table. So part D, what a coincidence, part D asks us to calculate d, the distance d, if x is equal to the value determined in part C. All right? So if part D will be kind of messy, so I will need a lot more space. Something I do not have much of. Okay, so it will be kind of messy. However, let's try to live with it. Okay, so we already know V. At this instant, since the table's frictionless, it will move with speed V equals 2.97. Why conservation of energy? We already solved for that. However, now we have to use conservation of momentum because there's a collision going on here. So momentum will get transferred. So if M1V1, and I'll just write the momentum statement just to make sure. PI equals PF. So momentum initials, momentum final. That goes to M1V1 plus M2V2. Then they both collide, so that results in M1 plus M2 times V. All right, so we're trying to find V. So M2 is at rest, so this is 0. So we're left with M1V1 equals M1 plus M2V. Okay, so if we want to find V, we solve and plug in to our little symbolic expression. You get, so you get, let's see, what do we get? Yes, M1V1 over M1 plus M2. That gets us, M1 is 4 kilograms. I don't know, I had trouble with figuring that out. And V1 is 2.97. So it's the instant before it collides, that's V1. Then we add the masses together. 4.0 kilograms, so it's 4.0 kilograms, and we get V is equal to, let me just plug into my calculator, 4 times this over here, that divided by 8, 1.49 meters per second. So that will be the velocity of the 2 block mass, the combined mass. All right, so over here, this combined mass will have V, just called final, to not confuse with that, 1.49, right? Now, if you want to save your time on some work, which I suggest you do, especially on the AP exam, well, keep in mind that as you are solving for time doesn't change. Why? It doesn't matter what the horizontal velocity is. If you look at how we solved for time only depends on the vertical distance, which is the same table, and G, which is the same. It's a constant. So we can immediately deduce that the time will be the same, 0.404 seconds. So we can just, I'm going to start to work here. So part D. So we can immediately find out that delta T is 0.404 seconds. Okay, so if that's 0.404 seconds, well, we can easily find the distance traveled. So Vx, delta x or delta t, you solve for delta x equals Vx delta t. Then you get delta x equals 1.49 meters per second and 0.404 seconds. And we get delta x is equal to we get exactly 0.6. 0.6 meters. You get exactly 0.6 meters if you use the exact value, or you get very close to 0.6 meters. All right. So this is 0.6 meters. Now for the conceptual part in part E. All right. Consider the system consisting of the spring, the blocks, and the table. How does the total mechanical energy E2 of the system just before the blocks leave the table compare to the total mechanical energy E1 of the system just before block A is released? Okay. So E1 is the mechanical energy of the system just before block A is released. E2 is after the blocks leave the table. So if you have a firm grasp of the conceptual knowledge of energy and momentum, you can easily find out that it is this. Over here, Y is E. The system loses energy because the collision between the two blocks, well, if they stick together, that is a perfectly inelastic collision. So because the collision between the two blocks is inelastic. Right? It's inelastic. They stick together. They will lose energy through sound and heat. They will lose energy because it's not elastic. You could also, if you want to do it the hard way, you could also find the kinetic energy right after collision and the kinetic energy before collision. Find the change in energy and check if it's zero. But you can just immediately realize that it's an inelastic collision and energy will not be conserved. And it will lose energy, it will not gain energy. All right, so we just solved this question. It was hard, but it could be done if you have firm grasp of kinematics and conservation of energy and conservation of momentum. Thanks for watching. If you have any questions, just leave a comment.